So, any other questions about anything? Okay. All right. Now, okay, let's talk about on chapter 26. Chapter 26. I'm going to start off with a problem. It's lenses in combination. Okay, now here's the deal. Here's the deal. When you do lens problems, because like here on chapter 26, I believe this guy is a, what is that guy? I hope he's lenses in combination. Does that make sense? Wait one. Gosh, dang. 24. Yeah, problem 60. This is a lenses in combination problem. Okay, let's take a look at how we would do lenses in combination. But first, on page 827 in my book, you've got this thing, for sign conventions for lenses. Okay, sign conventions for lenses, and it says that focal point is positive. That's a terrible marker. Focal point is positive for a converging lens. That marker is also terrible. Focal point is positive for a converging lens. Focal point, there we go. Focal point is negative for a diverging lens. All right, now, here's where it gets a little bit tricky. DO is positive. DO is positive if the object is to the left of the lens. Okay? All right? The distance of if it's a real object. It's a real object left of lens. Okay? It's a real object left of the lens. DO is negative if it's a virtual object to the right. If it's a virtual object to the right. Now that comes into play when you have lenses in combination. And then last but not least, we got our distance of the image, and it's positive. Now, unlike the mirror, remember you had a real image if it was in front of the mirror. Well, this is, since this is a lens and the light goes through it, you're going to have your real image should be behind the lens or to the right of the lens. By design, we set up all of our problems, and we'll do a lens in combination. Here's a lens. Here's a lens. And let's say it's 61. Here's our lens. And this is 61 millimeters apart, or 61 millimeters apart. We'll always start the problem by putting our object over here to start. Okay? We'll always put our object over here to start. All right? And to the left. Put your object to the left. So your image is positive for an image that is real and to the right. This is real to the right. And you've got DI is negative if it is virtual and to the left of the lens. Okay, because that would be a virtual image. All right. In other words, if I'm looking through this lens here and I don't see this object over here on this side of the lens, or if this object is projected to be on this side of the lens, that'd be a virtual object because the light rays coming from this guy are going to pass through that lens, unlike with a mirror where it'd be reflected back. All right? And then magnification, of course, is still the same. M is positive for an image that is upright, and M is negative for an image that is inverted. All right, so let's take a look at this problem. We're going to look at lenses, and you've got the good old lens equation is this. 1 over F equals 1 over DO plus 1 over DI. Now, when we do them in combination, basically what we're going to do is do the problem, and that's not distance of object, this is do the problem twice. Okay, so we're going to do the problem twice here. All right. Then I'll turn on the magic screen and we'll look at the eyeball and some of the magnification equations, which I don't give you on here, but I think it's good you know how your eyeball works. Okay. All right. Do the problem twice. So here's what we've got. We've got a object that is got an object. Here we go. The objective and eyepiece. Okay. So when you have lenses in combination, like for a microscope. Oh, I'm a roots man. There's a quarter. If you have a microscope, you've got two lenses. You've got your objective lens, and you've got your eyepiece lens. Now, I know all of you have taken biology, and don't they give you have to pass a microscope quiz before you can go on in lab? Did you have to do that? Yeah, that's kind of standard for biology class. So you already know all this stuff about the objective. Here's going to be our objective lens, and here's our eyepiece lens. Okay? All right, now what we're going to do is we're going to look at this little paramecium or whatever, and it is the focal length of the focal length of the objective is 15 millimeters. The focal length of the eyepiece is equal to 25.5 millimeters. Okay, and we're going to look at this distance of the object. Is positive. We're putting it to the left of the lens. It's positive. We're putting it 24.1 millimeters to the left of the lens. Okay? Now, the question is this. The question is this. And they're separated by a distance of 61 millimeters. The microscope is being used to examine an object that is 24.1 millimeters away. We've got all that in front of the objective. Find the final image distance. Okay? So what we're going to do is we're going to find the final image distance from the eyepiece. So we've got to do this problem twice. In other words, we're going to find DI for the objective. Okay? And that will put this guy right over here. We'll find DI for the objective, and it'll probably be upside down and right here. And then the DI for the objective, we're going to subtract from 60, or add it to 60. We'll subtract it from 61. And that will give us our DO for the eyepiece. Okay? This will give us our DO for the eyepiece. All right? And then we'll do the problem. Then we'll do that 1 over F equals 1 over DO plus 1 over DI again, and wind up with what our DI is. So we need our first DI here. We need the first distance image. We want to know this. How far away is he? We want to know this is our first one. This is our first question we're going to ask. We're going to do that first. Okay? Yeah. Pretty simple. We've got 1 over 15 equals 1 over 24.1 because it's positive. These are both converging lenses. By the way, they're both converging. Sorry. They're both converging lenses. So they're both positive. Plus 1 over DI. Okay? And you put that into your Bomar brain calculator. You all probably don't even remember the Bomar brain, do you? Came out in 1974. This is the first LCD fancy calculator. It could add, subtract, and do square roots and multiply. It was insane. All right, 1 divided by 15, and all the math teachers thought, oh, there goes the neighborhood. 1 divided by 24.1. They didn't realize that teaching that mundane crap was what was keeping students from liking math, so that calculator's a good thing. All right, 39.7. So DI, once you do all that, you get 39.7 millimeters. Okay, now that's what this is. So now, let's go ahead and find the magnification. That first magnification then would be negative DI over DO. So we've got, turns out to be positive, 39.7 millimeters divided by 24.1 millimeters. And so our first magnification is equal to 1.65. Negative. He's upside down. Okay? Now, let's do it again to find out his final DI. Okay? So now what we're going to do is we're going to find this DI that's going to be, this is the second part. Oh boy, second part. He's going to be way over here somewhere, away from that. That's the DI for the second part. So, we just do the same thing again. But this time, we need the distance of the object is 61 minus 39.7. Away. He's this far away. That's our new distance from the eyepiece. Okay? Which comes out to be what? 20.3 millimeters? So we just do that again. We go 1 over FE equals 1 over DO for the eyepiece plus 1 over DI. And we come up with 1 over FE minus 1 over DOE equals 1 over DI. And when you do that, you come up with about negative 130 roughly. I got 129. They got 130 in the book. You wind up with negative 130 millimeters for your DI. Oh, this is 21 point. This is 21 point. Oh, yeah, 61, not 60. Good. Thanks. That's probably why I got it. No. Okay. Negative 130 is what DI actually comes out to be. Not 1 over DI, but this DI by itself just comes out to be negative 130. So let's find that second magnification. The second magnification then is equal to negative 130 over 21.3. And that's about 6.5. Positive 6.5. And so the overall magnification, of this thing, this wasn't what they asked for. This was actually when we're done. That was the actual answer. But the overall magnification is equal to just M1 times M2. It equals M1 times M2. So you get negative 1.65 times positive 6.5. And it's about 10. It's about 10 times magnification. Okay, so it's not set on a very powerful setting. But as you can see, if you want to increase, you've got to increase the focal length to increase the magnification. Get this guy really big. Right? Okay. There you go. That's lenses in combo. Now, let's talk about the eyeball. That'd be a good thing to talk about. Okay, so I'm going to get everything hooked up here. We're going to go to the laser light show. I kind of use that. I use this a lot more when we're doing optics because the pictures are prettier than what I can do on the board. All right, so let's go ahead and lower. Lower this. I should have turned this on. Should have been waiting for this one. My AV skills are wanting, I think. Okay, this is kind of one of those parts that won't be testable. So right away you go, okay, my brain shut down now. But this is kind of interesting, I think. The human eyeball. Hopefully it'll come on here in a minute. And I can find it. Yeah. done all this, we've done all that, done all this, we've done all that. We just did that one. That's what we just did. Here we go. All right. Now, there. All right. Anatomy lesson. You all probably know more about this than I do. All right. Now, here's what happens. Here's what happens. You've got two things with your eye. Okay. You've got a near point and you've got a far point. For most normal people who don't, well, most people, a lot of people need glasses, but to have perfect vision, your far point is out at infinity for the most part, especially when you're talking about the distance between the lens and the retina, okay? And I can see on a clear night, if it's at the right place, I can see Venus, okay? Now that's a long ways away, right? You can see Venus, right? That little point of light out there. You can also see the moon, okay? So if you think of the moon as 3 times 10 to the 6 meters away, and this is, we're talking millimeters, all right? The far point's pretty much out at infinity, okay? And that's when your ciliary, right, ciliary muscle is relaxed, completely relaxed. When you look at something far away, your ciliary muscle is completely relaxed, okay? But then, when you're reading something, that's called the near point, okay? All right? So the near point is the point nearest the eye an object can be placed to produce a sharp image on the retina, okay? So the near point is where you hold things so that you can read them. So for an average 20 to 25-year-old, like most of you all, it's at about 25 centimeters, about 10 inches. For me, it's about 60 inches, okay? Or about 60 centimeters. And once you turn 60, it can be all the way out to 500 centimeters. So your arms don't get long enough anymore and you need glasses, all right, to be able to read. Okay, so that's the near point. And that's when this muscle is completely contracted, okay? That's when that muscle is completely contracted. So that gives you your near point. Your near point is when that's completely contracted. So what's that contracting do? It changes the focal length of the lens, okay? Changes the focal length of the lens when it contracts, and so that's how the eyeball works. It works just like any lens. Or we can say that a lens works like the eyeball, since that came first before we started grounding glass, stuff like that. Okay? So here you go. All right. Now, there is all this refraction that takes place in the lens, because you got the aqueous humor and you've got the actual lens and you got all this goop in the middle there. And so there is light being refracted about, and it puts that image, a distant image, is really small, and it's put on your retina. Just like when you look at Venus, it looks really small out there. It's this little dot of light, right? Okay? But if you held a penny up at arm's length, you go, ooh, that penny, it's 10 times bigger than Venus. According to your eyeball, it is, but you know better. All right. Okay. Now then, for nearsighted people, so what are we going to start with? We're going to start with nearsighted. Okay, nearsighted people can focus on nearby objects, but not far away objects. Okay? So those of us, when we get older, we actually become farsighted. We can focus on far objects, except my farsightedness is just going downhill rapidly. It's like every day it gets worse, it seems like. But anyway, but nearsightedness is when you can focus on nearby objects, but not far away. Your far point of your eye is not quite at infinity, okay? It's supposed to be out there pretty far, out at infinity, but yours is actually brought in a little bit And so therefore, what happens is this image is an aberration. It's not formed right on your retina. So it looks blurry. All right? And so you put a little diverging lens on there. Right? You go to your optician, and you put a diverging lens. He goes, oh, here's what you need. You need a diverging lens. Okay? And then that will change the thing so that the image is formed right on the retina. And basically what it does is it brings Venus from infinity up to the far point of your eye so that you can make it out. Okay? A little bit clearer. Or the moon. Not the moon, not like a harvest moon, because we all can see that, but like when the moon is a little bit, is in the 7th house. No. But it is when the moon's a little bit further out. Okay, by the way, there's plenty of seats for Astronomy 350 if anybody's interested. And you want to get that physics minor. Okay. Anybody out there in TV land, you want to get a physics minor? All right. Example. Oh, eyeglasses. Oh, we're not going to do any of the examples. We're going to move on. Okay. All right, farsightedness. Farsightedness. Farsightedness, the near point of the eye is too far away. The near point of the eye is too far away, okay? And so, and farsightedness is when your lens is completely contracted as much as it can be, okay? And I believe, I don't know, maybe some of you that have had all that anatomy and everything that you all have had can tell me, but that is, you can't control that, right? That's just a that's, right? Your lens, you can't go, even when you squint, I don't think that really helps. So, but anyway, so what happens is, you wind up with the sharp image is way behind the retina, okay? So you got this sharp image way behind the retina, and so you got another aberration. You can't see. It's all blurry. And so what it basically does is it brings the near point of the eye in out to where it's supposed to be, and you've got it. Okay? So there's how the eyeball works, roughly in 5 minutes. There. Now you can all go be ophthalmologists or optometrists. Okay. Okay, now, let's talk a little bit about angular magnification and magnifying glass. This is one of those things where you take science so that you can be a better parent. So when your kids ask you, well, how does this magnifying glass work? Kind of, and you can tell them, okay? Okay, so the size of the image on the retina tells you how big it is. Okay, so you got that angle. All right, now, here's what we do with that. Okay, so you remember all this? Little trig here. You've got the arc length, theta is in radians. The arc length is equal to the radius times, remember, arc theta. And so you take the length of the arc is divided by the arc length divided by the radius, and that gives you the angle theta. And for the most part, the angle theta is real close to the height of the object. Okay, so right here, you've got this angle that's putting it on the back of the retina, back over here, same angle, all right? And that gives you the height of the object. Now, if you need that object to be taller, what you do is you put a lens in front of it. You put a magnifying lens in front of it, okay? And so now, it's going to form a sharp object on your retina, but we've moved this thing closer. It's like we've moved our eye closer, and so now this angle gets bigger, and so we've got a virtual image. It's a virtual image that's back here that looks much taller than the actual height. You can also reverse the process with a diverging lens. I mean, it looks smaller, but it would actually be a virtual image that would appear in front. Okay, and the magnification Here's angular magnification. You take the new angle theta divided by the old angle. Here's the theta prime. Take this theta divided by that theta, and that's your magnification. All right, for just a regular magnifying glass, here it is. It's 1 over the focal length of the magnifying glass divided by the distance of the image. Okay? You might be going, well, what the heck happened to the distance of the object? I'll tell you. The distance of the object is equal to this. 1 over f minus 1 over di. That is the distance of the object. And so for a magnifying glass, another equation for it is m divided by is n, which is the near point. Oh, by the way, that n is the near point of your eye. So with certain people, if you ever watch people with a magnifying glass, they put it in different places, right? Like I'd have it here. Jared might move it a little bit closer or something like that, because it's up to your near point. That's where you put that. Okay? So there you go. There's angular magnification. All right. Now, let's just talk a little bit about compound microscopes. We've already seen this equation. I just want to tell you what, again, n is the near point of the eye. I just want to tell you what some of these variables are that are up here on the way you determine the magnification of a microscope. I didn't assign you any of these problems, and it won't be on your in-class group test we're going to take on Wednesday. By the way, Friday, I have to do RU orientation day. So Wednesday will be the last time we meet, a week from today, okay? I know that's sad. Everything just like today's your last lab. And I know you're going to go in there and Osan's going to miss you all. But anyway.
So we don't get the ice cream?
What's that? No, sorry. Sorry, I got to go do room day. But anyway, so make travel plans if you want, those kinds of things. So if you need to go somewhere, you can fly on Wednesday night if you want to, right? Okay, so anyway, but that also means by 1 o'clock Friday, I need all your homework done, okay? And I'll put the last 3 assignments, which is only 10 problems or 11 problems all together on this other thing. Okay. So anyway, L is the distance from this lens to this lens, from the eyepiece to the objective piece, okay? And then, of course, FE and FO are your the focal length of the eyepiece and focal length of the objective, and N is the near, again, the near point of the eye. So N will vary depending upon individual. And they probably mean that N for a normal 20/20 vision person, so you can probably consider that at about 25 centimeters. Okay. So what else have we got here? Oh yeah, then last but not least, the good old telescope. The good old telescope. You got these lenses in combination again. You got your objective, you got your eyepiece. All right. Forms the first image, way out here at the far point. So there is no end point, there is no end here. Forms the first image. The length is the length between the two things, and then it forms the final image near infinity, which is upside down. And it's out there near infinity because if we're looking, like I said, if we're looking at Venus or if we're looking at, it's really cool looking through a telescope at Saturn because it actually looks like it does in the cartoons, little rings around it. But it's way out there. It's out there near infinity. Especially when you're talking about this distance here is going to be, in less than a meter. And so the magnification for it is so to increase the magnification, you either change the focal length of the eyepiece, you either lower the focal distance of the eyepiece or increase the focal distance of the objective. And it's much easier to change this guy. And you do that by twisting the thing. All right. Okay, so that's it on chapter 26. Chapter 26. Now, everybody's favorite chapter. Chapter 27, we're going to end with thin film. All right? Going to end with the thin film experiment. Now, this chapter's not too bad. It's not too bad. There are worse things that could happen. I don't know any off the top of my head, but from the beginning. Okay. Interference. And let's get that arrow out of the way. All right. Interference in the wave nature of light. It's very important that you understand. All right. How many of you have ever noticed that when you have a flashlight, it's a regular flashlight, and you put like a round circle, like this quarter. Put this quarter in front of the flashlight. What happens on the screen with the flashlight? The screen forms these funny-looking rings, concentric rings. Some are bright, some are dark, and you'd think that it would just be a dark spot right in the middle, right? But that's not the way it looks at all. And it doesn't look that way because light is diffracted and it moves in a wave, all right? Because of the diffraction of light, it moves, it is a wave, all right? Now, good old Isaac Newton thought that there were like little photon type things or little light particles, and that was it. Now, we found due to Einstein's photoelectric effect and all those other things that light is both. There's a particle and a wave. By the way, you're a wave, too. You just don't diffract very much, all right? Okay, so here we go. When two or more light waves pass, now they have to be coherent light for this to really work. Otherwise, you get something different. Well, you get. I'll explain it in a minute. We're going to do it coherent light. Let's say we got lasers. All right. Now then, for two waves, they're going to have. In other words, you got one. Let's say you're out here at point P. You're bobbing in the Lake of the Ozarks. It's nice and calm. Okay. You're out there swimming, and then two bass boats go whizzing by. One on one side, one on the other. Okay? Now, two things can happen. Those waves can either interfere with each other as they come in, as the wake of those two boats are coming in at you. They can either, one will be down and one will be up, and so they'll cancel each other out, or they can be in phase and really get doubled. Okay? So if they're in phase, that's constructive interference, and you get double the amplitude. All right? Okay? And so the actual wavelength is equal to m times lambda. All right? Okay? And say, so this wavelength, this length here is actually 2 1/4 lambdas, and this wavelength is 3 1/4 because it's 1, 2, 3 1/4. Okay? Wavelength. And so when you subtract those two, you get a nice number of 1 right here. It'll always be an integer number, 0, 1, 2, 3. Now then, that's constructive interference. So in other words, if this was a green light, and this was a green light, and you're right here on that screen, and that screen is right there, you're going to see a green light. Okay? You're going to see a green light. Now, the next thing that happens is this. Get good old destructive interference. So you take this wavelength minus this wavelength. Ooh. Straight line. It's dark. It's dark. The light's not coming through. You get a little destructive interference. Again, but notice. Again, M is at 0. It starts with 0, 1, 2, 3, and goes on out to however many fringes that you want. And I'll discuss what fringes are here in a minute. But these are at a half from each other. Okay? All right, so let's take a look at what all this means. Here's the next good picture of what all this actually means. Okay? If constructive interference is to continue occurring at a point, the sources of light must be coherent. In other words, it must be like lasers. And so coherent light maintains a constant phase relation. But anyway, let's take a look. Now this is the big. This is big. This is good old Young's double slit experiment. Okay? This good old Young's double slit experiment. Now, if light didn't behave like a wave, this tells us that light behaves like a wave. If light didn't behave like a wave, then if I shot all these photons through here, this slit, then I'd just get a slit right here in the middle, right? But I don't. It all spreads out. It's going, whoa, it diffracts out. So it behaves like a wave, all right? Okay? The easiest wave that I can think of is like water, which is why we call them waves too. In other words, if you've got a crack if the bathtub is flooding and you've got a crack in the bathroom door, does the water just come out in the width of that crack? No. What's it do? As soon as it gets through the crack, it diffracts out and goes all over, right? Same thing. Same thing. So it moves like a wave. Now, here's what happens. Light comes through here, hits this slit, and then it diffracts out, and you get all these dark fringes and bright fringes. All right? You get all these dark fringes and bright fringes. Now, the bright fringes go with constructive interference. The dark fringes go with destructive interference. All right? So where it's dark, the wavelengths are out of phase. Where it's bright, the wavelengths are in phase. And right in the middle, they're the most intense. And that's where m equals 0, which is, I think, what they show us here. Actually, they don't, but they show kind of the mathematics of it, which we're not going to worry about too much. And then right here. Here's the different intensity levels. So right here, where m is equal to 0, m equals 1, 2, 3. M is a half, m is 3 halves, m is 5 halves, m is 7 halves. Okay, m is 1, 2, 3, 1 half, 3 halves, 5 halves, 7 halves. Okay, and this is bright fringe 1, 2, and 3, and he's 0 right smack dab in the middle. Okay, 0 right there in the middle. All right, so there. And it's because of Young's double slit experiment we have CD and DVD players. Because we can adjust the wavelength, which adjusts the frequencies, and we can code information on there, and so we get different pictures and different sound. Yes?
Can you get a perfect ledger that doesn't diffract?
I don't think so. Because it's still a wave, it's still a light. Okay. I'll double check on that. Double check. It's a good question. All right. Okay, so here's how you find the angle, okay? Here's how you find the angle that they're diffracting, okay? Here's the angle of diffraction. All right, for bright fringes, it's m. It's the sine of the angle is equal to m times lambda over d. D in this case is the diameter of the slits. Okay, the distance between the two slits, not the diameter of the slits. I'm sorry, I was getting into something else there. It's the distance of between the two slits. Okay. So those, now then, for your homework, you've got a little question, question number 2, ask you, okay, you've got, it'll give you the wavelength of the light We'll say, okay, it's got the wavelength. The slit is this. And you want to find what the angle is at the third bright fringe. Oh, okay. So they give you lambda. They tell you what D is. You plug a 3 in here. Boom. Take the inverse sine of that. Ta-da! You've got the angle of what it is. All right? So there's things we could... And where's like the fourth, if you wanted to find like the fourth right fringe, that would be at 1/2, then here, 1/2, 3/2, 1, 2, 5, 7 halves. Okay? From right here. 7 halves. Those kinds of things. That's the way your homework is decided. It's just going to be using that equation. All right. And here's an example. Here's an example of, okay, we've got this distance between the fringes is this, which is 1.2 times 10 to the, that's a -4 meters, all right? It looks fairly clear on here, but I don't know there. All right, and m equals 3, m equals 0, m equals 3. All right, what they want you to do is they want you to find out what y is. What y is. Well, did they give us lambda? Yep, they gave us lambda. Now this one's kind of annoying because you're going to have to change that lambda to 664 times 10 to the -9 meters. Okay? You've got to put everything in meters. All right, we can find y. Once we find this angle, y is pretty easy to find because once again, we'll just use the tangent of that angle to find y. Okay. And so what, is that what they do? Yeah. They go, okay, let's just take theta is equal to the inverse sine of m over lambda times the distance between the two. Gave us the lambda. Third right fringe, this. We've got this dinky little angle here. Y over L equals the tangent of that dinky little angle, so you multiply that out. And it looks like the distance here is 0.456. So, if you're doing your take-home test, or not your take-home test, your in-class test, and before you guys start fighting with each other, and it says, okay, the fourth right fringe is this long, what's the wavelength? Okay, the screen is this far away, fourth right fringe is this long, you could work that one backwards, because you could figure out what the wavelength is. If they gave you D, and you had 4, you'd be able to find lambda. Okay, if you knew that what this y was. All right. Okay. That might be kind of a little tricky. Okay. Last thing before we get into the thin slit, into the thin film, which is actually kind of cool stuff. All right. So here shows a photograph. If we just had a regular flashlight or something, or an incandescent bulb. All right. Now notice what happens. It breaks the slit because of the wave nature and because of interference. It breaks the light down into its different component parts. Okay, into starting all the way over. Where's it end? With the red and yellow light. And the central fringe is the brightest because this is where it's most intense. So it's still white. It's washed out due to all the other interferences. Okay. All right, now let's take a look at why soap bubbles. Here's another question that you might get as a parent. Why are soap bubbles so colorful? Okay, here we go. This is why. And we'll get to these problems. We'll get to a problem here in a minute. Okay? Got it. Here's gasoline. If you've ever noticed gasoline floating on top of water, if you look at it, it's got kind of a rainbow type effect. That's due to the thin film refraction and the interference that's taking place. Okay? Because of reflection and refraction, 2 light waves enter the eye when light shines on a thin film of gasoline floating on a thick layer of water. Okay, so now what we do, because the extra distance traveled here can be interference, there can be interference between the two waves. All right, so here's what happens. Here's what happens. We're going to look at these boundaries. We're going to look at right here, and we're going to look at right here. Okay? Now, this next slide tells you how to break down what's going on at these two boundaries. All right? There it goes. Oh, by the way, the film, which you know, the film is going to equal the wavelength in a vacuum divided by whatever the refractive index of the film is. Okay? So in this case, it would be whatever the wavelength is. Let's say it's 664 nanometers for a red light, and we divide it by the 1.4 for gasoline, and that's its wavelength in the film. Now, here's the deal. Okay, between boundaries, when light travels through a material, here's the deal. When light travels through a material with a smaller refractive index towards a material with a larger, so if we're going from air to gasoline, reflection at the boundary occurs along with a phase change that is equivalent to 1/2 the wavelength in the film. So it's 1/2 lambda film, okay? But, so, let's go back. So right here, at this boundary, we're going from 0 to 1.4. So right here at this boundary, we get lambda, 1/2 lambda film. Now then, as we go from, at this boundary, we're going from 1.4 to 1.33, we get 0. 0. Okay, phase shift, phase change. They call it phase change, phase shift, same. All right. Okay, now, let's do a problem. And I'm going to actually work this out on the blackboard. We're going to do 2 problems, and that'll be it for the day. Because we're zipping along through optics. All right, so here's what we're going to do. We're going to do this problem right here. I'll show you, there's a technique to working these problems, and you've got problem 10 on your homework is just like this one, or real close. And what we're going to, and you'll also have one on your group test on Wednesday. All right, so a thin film of gasoline floats on a puddle of water. Sunlight falls almost perpendicularly. We could say it's almost perpendicular, so that when it bounces, when it goes through, when it bounces through, we could say that we've got thickness T plus T, so we always say 2T. And I'll show you in a minute how this works. And the film is, has a yellow hue because the destructive interference eliminates the color blue from the reflected light. Okay, so we're going to look at destructive interference for 469, all right? And we've got the 2 indexes of refraction. All right, so we're going to turn that off. Okay. Raise the checkered flag, or surrender flag by now. All right, here we go. And then tomorrow we'll finish, we'll talk about diffraction, and we'll talk about resolving power, which is kind of cool, because I do give you the problem. Problem 28 is about a hunter who is bragging about having how his eyeballs are so sharp and everything. And you'll see with resolving power why eagles can see, why there is such a thing as having an eagle eye. You can make things out. Okay, but here we go. Let's do this thin film problem and call it a day. All right. Here we go. Now, here's the deal. You've got, okay. Now, they want to know what the minimum thickness of this is for having destructive interference. Okay, well, first of all, we know this. Well, I know this. You probably all don't know this because this is the first time you've seen this stuff 10 minutes ago. All right? destructive interference looks like this, is equal to M plus 1/2 times lambda of the film. That's destructive interference. So we'll just take each of these where M equals 0, 1, 2, 3, on out. We'll just jot down the first 3 of those. So we've got, when M is 0, we've got 1/2 lambda of the film, or we have 3/2 lambda of the film. And this is where you set these up each time. You got 5/2 lambda of the film. Okay. We'll just set up the first 3. Now, if it said it was going to be constructive interference, we wouldn't put the halves here. We'd put 0, lambda film, 2 lambda film, 3 lambda film. Okay? Now we got to figure out what we put on the left side. Destructive interference tells me what to put on the right side of the equation. The physics tells me what to put on the left side. Okay? All right, now, here's what's going on. You got 1.4 gas, 1.33 water, 1.00 air. All right, so the first one comes in. We're going to take a look at this guy. And we know that this has a thickness of T. So right away, we'll just put in 2T, because it's going to come in, it's going to go boink, boink like this. So, and because it's almost perpendicular, pretty much perpendicular for our purposes, that's a T and a T, so that's 2T. Goes right here. Plus, now's when we figure out the phase shifts. Right here, this part right here is where we figure out the phase change. It's where we're going to figure out what the phase change is. So here we go. Okay, so you've got a reflection. We're going to look at this boundary and this boundary. This one will be for 1, and this one will be for 2. Okay, and our eyeball is right here. Okay? All right. Now, as it's going from 1 to 1.4, is that a phase shift change of 1/2 or of 1? Or of 0, sorry. Half, because we're going from lesser to greater, so we got a phase change of 1/2. So for 1, we'll just go ahead and put 1/2 lambda film. And now let's look at 2. Let's see if we have to add 2 on there. This is going from 1.4 to 1.33. So what is that one? 0. So this one was 1/2 lambda film, and this one was 0. So we're done with setting up our equation. And what we're trying to find is the minimum thickness, in case you forgot. Minimum T. We're trying to find the minimum of T. Okay? So what we do is, now we just do some simple algebra. That's all we got to do. That's all we've got to do. Just do some simple algebra, and we go, oh, okay. Well, we've got 2T. So we're going to subtract this 1/2 lambda film from each side of the equation. So we're going to subtract 1/2 lambda film here. Ooh, if I do that, what's 1/2 lambda film minus 1/2 lambda film? 0. So my thickness is 0. That's no good, because I know there's gasoline there, so it can't go at 0. So let's go on to the next one. Subtract 1/2 lambda film from this. So that one we're not going to do. Let's subtract 1/2 lambda film from this side. Ah! This will give me my, so I take 3/2 minus 1/2. I wind up with 1 lambda film. Or basically M equals 1 right here. Is what I wound up with. M equals 1. Hey, I'm done. Because T is equal to lambda film divided by 2. Okay? Where lambda of the film is equal to lambda in a vacuum divided by N of the film. So in this case, they told me it's 469 times 10 to the negative 9 meters. Oh, we could just leave it as nanometers. We could just leave it as nanometers because the thickness, I would think that the thickness of the film, since this is just a number, doesn't have the units to it, I would think that the thickness of the film would make more sense in nanometers, or just as much sense in nanometers as it would in meters. Divided by 1.4. Okay? That's the way that's done. I'm pretty sure. I'm not going to hold it up there on the screen. Yeah! You did it right. Yay. Good. Good, good, good. It's a little confusing the first time you see it, but it's not bad. Now, if we'd have had destructive or constructive interference, we'd have gone through the same thing, gone through the same, you do your analysis, to get your left side of the equation, do your analysis over here. And we've done enough. I'll start with here, and we'll do resolving power. Then we'll finally get to my favorite subject in 210 and 220, special relativity on Friday. And we'll end on Monday. And we'll take our quiz, our in-group class on Wednesday, and we will part company. We'll be done. Done, done, done. All right. Okay, so go have fun and laugh. Go forth and prosper.